Hello, my name is Oliver Maiß, and I head the Research and Development Department here at ECOROLL AG. Today I'd like to compare two different mechanical surface processing methods for you, namely shot peening and deep rolling. Mechanical surface treatment processes are generally special processes designed to perform a post-treatment of the surface after mechanical production, specifically through mechanical stress, with the aim of improving the component's surface and subsurface area properties. There are various processes that can be used for this purpose. For one, there's roller burnishing and deep rolling, which are also frequently referred to as roller burnishing. There's machine hammer peening, and then there's the probably very widespread and most well-known process, ball shot peening. In shot peening, a blasting medium is used, which can be various balls or wire elements, essentially just cut wires that are then very sharp-edged. It could be glass beads, or it could be hardened steel balls. So a wide variety of blasting media, also in different sizes, are shot onto a surface. Actually shot, this happens through a wide variety of blasting systems. This can happen with compressed air, or it can happen via centrifugal wheel technology. So there are various ways to accelerate this blasting medium and shoot it onto the surface. When it hits the surface, it creates a mechanical change there upon impact of the blasting medium at a single point. And now, of course, I have many tiny balls hitting there, and these many tiny balls create, so to speak, an area in which I have, impacts. Of course, with ball shot peening, I have to ensure that I cover this area completely and have no elements or surface elements that haven't been peened or that have been peened with a different intensity. That's why shot peening is actually a very stochastic process at this point, which I also have to prove afterwards that I've peened all areas uniformly. When the balls hit there, they create compressive residual stress, they create cold work, they simply change the component at that point through this mechanical impact. If we look at that, compressive residual stresses are created in the surface, which can also be quite high. So we really create very high compressive residual stress here, sometimes in the range of the maximum that a material can withstand or even sustain in terms of compressive residual stress. Through the impact of the blasting media and this mechanical change, this plastic flow, we create cold work by increasing the dislocation density. And all of this together then leads in the end to the fact that, as a rule, the service life of our components is significantly increased. That's also the reason why shot peening is frequently done. It's used a lot for turbine blades, for example. It's used for gears. These are typical components that are shot peened to further increase the mechanical load capacity of the component. With shot peening, the Wöhler curve is shifted, so we have a significantly higher fatigue limit here. This means we shift the Wöhler curve upwards, and the slope of the Wöhler line remains relatively constant in this test here. There are differences there too, depending on notch geometries and such. It has other effects, but that is actually always the general correlation. My fatigue strength goes up. How much more I have to find out through the process. I can also play around with the process parameters a bit, but basically I shift the fatigue limit upwards. If I compare this with deep rolling the process, I have explained the process very often on this channel, so just a quick summary. In deep rolling, I have a roller that is much, much larger than the ball in shot peening. And this rolling body is pressed onto the surface with a defined force and then rolls continuously on this surface. This means we have a continuous change in my subsurface area. This is a very defined process compared to ball shot peening. One could perhaps equate geometrically defined machining with geometrically undefined machining a bit. One could say shot peening is basically the grinding of the machining. Deep rolling is then the turning from the machining. In comparison, the compressive residual stresses I achieve with deep rolling are in a similar range, right? So the maximum compressive residual stresses are not that much higher through deep rolling, but due to the larger ball geometry or rolling body geometry, I have a much, much greater depth of indentation of my residual stress, right? The residual stresses really reach much, much deeper into the surface. This can be explained relatively easily via the Hertzian contact. Yes, right? Larger contact partners, greater depth effect of the Hertzian pressure, and that then also affects the residual stresses. And if we transfer that to the Wöhler curve I just showed, then you can see, as shown here on the right, that the fatigue limit can be on a completely different level through deep rolling compared to shot peening. So here we have a much, much higher increase in fatigue strength again. It even looks almost as if we have almost no drop in fatigue life, right? So the fatigue life line also remains here or becomes much, much flatter here. Yes? and my component can simply withstand much, much higher loads than if I were to only use shot peening on the component. Now, shot peening naturally also has its advantages. Shot peening ball is very flexible. I can get to, yes, components that are sometimes difficult to deep roll, such as the gear or something. But with deep rolling, I have the advantage that I can carry out the process directly on the machine tool. I don't need an additional shot peening system that might be standing next to it or perhaps at a supplier, but I can simply clamp my deep rolling tool into my lathe and carry out the deep rolling process directly on the lathe. With that, I'm at the end of this short video. Thank you very much for your attention. Feel free to share this video, like this video, and if you have any questions, you can contact me or my colleagues at ECOROLL AG.